Hey folks, in today's video, we're going to talk about how liquid clustering makes streaming merges simpler and also improve the P99 latency. For those who are new here, I'm Sony, the Canadian data guy. I've spent over 10 years at Amazon and Databricks, and now I work as a specialist architect. Each week, me and my team, we publish a deep technical blog without any marketing fluff and just engineering insights and what we are seeing on the field. If that's the content which speaks to you, then check out databricks.com. Okay, so prior to liquid clustering and row level concurrency, when you are doing merges in a streaming fashion every day, what you would do is you'll have a streaming job running. Uh, every patch, you'll make a for each patch call. Inside that for each patch call, you'll run the merge operation. And after every n batches, you'll have to pause your stream and actually run optimize. Now, why would you have to run optimize while pausing? That's because optimize and the streaming merge would conflict with each other. The other reason you might want to run optimize in parallel was if you want merges to be very fast, the data needs to be clustered in a way. So that those were the two reasons why people would do this. Now with liquid clustering and row level concurrency, thankfully you don't have to do this. So essentially your streaming jobs can keep opening up for each batches, and inside that for each batch, you can go and merge into your delta table. And in parallel, you can leave it to predictive optimization to figure out when it's time to run optimize on your table. And these two operations are independent of each other, and that's the benefit which you're getting. So if you are running optimize after every 100 batches, essentially the time the optimize needed to run, the latency would go higher, right? Because no new data is arriving. So that's why your P99 would go high. And now, because now they can be done in parallel, that's why your P99 would go lower. The other benefit you're going to have is that your code would become simpler because previously, if you had a streaming job, you write the merge followed by an optimize. Okay. Now, how does this get achieved? So let's get into that. We'll have to cover two concepts here. One is deletion vectors, and the other concept is row level concurrency. And once we combine both of them together, you will see the benefit here. Okay. So the first concept we're going to talk about is deletion vectors. So how does deletion vectors work behind the scenes? Deletion vectors basically creates a binary file. So if you have a delta table, you try to update a few rows, say you're trying to delete some rows. Now it could be a literal delete or an update, no matter what the case. Someone needs to remember that this file has been updated. And because S3 and ADLS does not allow update operations, any object written on it is immutable. So a new file has to be written. And the new file has to be very light. So this new file which is written is the deletion vector file, which is binary behind the scenes, and it's a bitmap. So essentially, imagine you have a Parquet file and the rows written in that Parquet file. What we are going to do is when we write our deletion vector, aka binary, which stores the bitmap inside it, the bitmap is going to remember which of these rows are active. So when you read back deletion vector file and Parquet file together, you get to know which rows are active. That's the magic here. That's how things are in action. It's a three-step process. You can read about it. This is called merge on read. It can be also referred as soft deletes. So essentially, the reader who is reading your delta table, they know how to read a delta table. So you don't need to know all the nuances, which always, as a good data engineer, you need to see through the noise, right? If someone says, hey, this feature exists, then the question should be, hey, how does the feature exist? So this is the implementation detail behind deletion vectors. Again, I'll leave a link in the reference where you can read more. So this is how deletes or updates are achieved using deletion vectors. The second thing that we need is row tracking. So in a row tracking feature, every row inside your delta table gets a unique row ID and row commit version. So if you combine both of these concepts together, you will see the benefit. Okay. So before row level concurrency, what would happen? You can imagine there's a file A with 4 rows and deletion vectors is all zero, meaning all rows are active. Now, if you delete one row, essentially in the deletion vector, there would be a change and you mark in the deletion vector as that row 3 has been deleted. So that's just soft delete or deletion vectors in action. Now, next step. Suppose if you have two transactions trying to update different rows. So in this example, say T2 transaction trying to update row 0. Without row level concurrency, what would happen is if T1 has gone through, then T2 who is trying to update the same file would get conflict, it would be rejected. But if you add the row level concurrency features, which basically has the row ID and row commit version, it would recognize that T1 has committed and T2, when it's trying to commit the file, it will see something happened to this file. However, it impacted a different row. That's why I don't need to fail. That's why it can continue going on. So that's how the concepts are coming together. Hopefully you can see that once you have the deletion vector, which gives you soft deletes, meaning you don't have to rewrite the whole Parquet file. And then you add the concept of row level concurrency, which basically gives each row a row ID and row commit version. Then you can allow two transactions or multiple transactions to write to the same delta table, and they won't conflict with each other as long as they are altering different rows. Now, all this is the theory, but I like to see things in action. So I created a demo to prove that this works. So I have been running a job which is doing merge and optimize in parallel to prove this out. And I ran this experiment for 52 hours, which is roughly 7 days for the purposes of this video and my demo. So what's happening right now is we have a streaming job. This is my streaming data frame, which is creating 1,000 rows a second. It has 50% updates, 50% inserts, sorry, 10% update. So that's the ratio. This is configurable. So don't worry too much. And what happens is you have a streaming data frame and then you call a for each batch. And inside that for each batch, I'm basically running my merge. So if we go here, you will see that I'm running a merge on the delta table. And then in the prior world, after every n batches, I'll write a if condition here, which will say, hey, after every n batch IDs, let's run an optimize. But now that I'm using deletion vectors, row level currency, and stuff like that, I don't need to do it. My life is much simpler. So technically, your code would stop here. That's it. Like you just need to call a for each batch and run the merge, and then you'll have streaming merges. I'm running like 500 optimize in sequence, and then I'm running it at random intervals. Basically, I'm trying to force a conflict to happen. But as you can see, it's been like we have had like 46 optimize run, and yeah, it's running fine. Basically, the optimize and the merge are not conflicting with each other. So the theory is matching the practicality. And yeah, this is some code which is there to prove that this works. When you are doing this, and you actually can leave it to predictive optimization. So in the code which I showed you, I was manually running optimize in parallel just so that I can prove that, hey, this is can be done in parallel. But in reality, you can just leave it to predictive optimization to run optimize. So hopefully the concepts connect. And if you enjoyed this kind of a content, please keep following us on databricksters.com. Again, idea is to write clean, deep technical content without the marketing class. So whatever we are writing from the insights which we are seeing on the field. Me and my team write all kinds of content, data engineering, Gen AI, streaming, all those kinds of amazing things about Databricks. See you next week. Bye.